So I cannot show you the computer directly. Not show you the computer directly the numbers, but I can illustrate a simple example and do the calculations right here and show you the numbers. So let's do that kind of on the fly. I'm going to open MATLAB. Okay, I'm going to open MATLAB. Like this, okay? And then I'm going to show you this. We don't have to do all the stuff on the identification to show the point. So let's just say that this system has equal stiffnesses equal to 1. That's the easiest number. So let's say K is equal to 1 in every floor. Okay, so the stiffness matrix of this structure then, let's assume that we had sensors in all the levels, or that we were able to expand the matrix so that we were measuring everywhere. So now that we are measuring at all positions, we have the matrix 4 by 4, and the stiffness matrix would be 2 minus 1 0 0 minus 1 0 0 2 minus 1 0 minus 1 0 2 minus 1 minus 1 1, right? So that's the stiffness in the reference state. Now, I don't know this stiffness in reality, right? What I know is the flexibility, because what I am saying is that the flexibility in the reference state is the inverse of that, and so I'm going to input it right here as 2 minus 1 0 0 minus 1 2 minus 1 0 0 minus 1 2 minus 1, and my last row 0 0 minus 1 and 1. I close. That's my K. My inverse of K is this 1 1 1 1 1 2 2 2. Yeah, then it should be 1 2 3 3, as one can see from logic, and then 1 2 3 4, right? This is the flexibility matrix. Makes sense, right? If you can see it from flexibility right away. Apply unit load, you get a 1 1 1 1 everywhere. You put it here, you get 1 2 and so on. So that's the flexibility matrix, which we would obtain from vibration data. Again, here I'm using all the coordinates, but the technique doesn't care that you have all the coordinates. It works with whatever you have. Now, let's assume that this spring here gets damaged. Now, if this, or this floor gets damaged, now, because I'm using theory, it doesn't really matter how much damage I put, right? But I'm going to say, yeah, okay, let's just say that now it's 0.9. So the K in the damage state will be, you know, we lost 10% here. So we have now 1.9, what is it, minus 1 0 0, and then that's when we move it here, then everything else stays the same, right? Minus 1 0 0 2 minus 1 0 minus 1 0 minus another 2, another minus 1 and 1, right? So that's our stiffness matrix, K in the damaged state. So I will say KD is equal to K, and then KD 1 1 is equal to 1.9 instead of 2, and then the inverse of KD is something that is F in the damaged state is equal to 1.11, and then it's 1.11 repeated 4 times, then the next number is 1.11, and then 2.11, which gets repeated down, then the next number is 1.11, 2.11, and 3.11, which gets repeated 1. And then the last one is, of course, 1.11, 2.11, 3.11, and 4.11, right? And these things go on with more points. So if we take the difference between FD and FR, we get delta F, right? And the delta F in this case, you can calculate yourself, right? I'm just going to give right away actually it's 4 columns of equal numbers, just 0.111 everywhere, right? So the DF is just 0.11111, all the 4 columns. And if we do the singular value decomposition, of DF, right, we get the singular values as expected. There's only one damage, right, on the first floor. So the singular values are 0.44 and then 0, 0, 0. Okay? That means that these last 3 columns of the V are damage locating vectors. I am looking at the screen here and looking at what the last 3 columns are. And I see that this column is 0, 0, and 0.707 and minus 0.707. The next column is 0.32 minus 0.86. I'm rounding to 2 digits. 0.27 and 0.27. And the third column is 0.8. I'm writing it here. The next one is 0.03. The 0.8 was 0.8049, so 0.03 minus 0.42 and minus 0.42. Okay, so those are the numbers that we get for the 3 columns which are associated with the 0 singular values. Now we take our 1, 2, 3, 4 stories and we look at the loading, right? So the first loading is 0 at 1, 0 at 2, 0.707 and minus 0.707. If we look at the shear plot, because this shear building, we get 0.707, well, we get 0.707 negative, goes like that, then 0, and that's it, right? Now the damage was here on the first floor. It's correct because it's 0, but you can see that 2 and 3 also have zeros. Now we look at the next one, and the next one is 0.32. Oops, sorry, here, 0.32. Next level is minus 0.86. To the left, 0.27 and 0.27. So the shear plot for that is 0.27, goes down, adds another 0.27, that's 0.54, goes down like this, then subtracts 0.86, which is 0.86 minus 0.54 is minus 0.32. And then it goes like this, and then boom, 0. Okay? So we see that the second damage locating vector is itself perfectly specifying because it only has one non-zero entry, which is the first one, right? But it just reinforces what this one also, I mean, this one tells you everything, this one reinforces it. And if we look at the last one, which is 0.8 to the right, and then 0.03 backwards. I keep putting it in the wrong place. I'm sorry. 0.8 to the right, 0.03 to the right, 0.42 to the left, and 0.42 to the left. And so we see that the distribution of the shear forces is minus 0.42, minus 0.84, and then a 0.03 is minus 0.81, and then 0.8 kills it here, right? So again, this one is full self-identifying, just first floor. This one is just the first. This one is this, okay? In all cases, we find that the damage was located on level number 1. Now, in a situation such as this, if the structure is simple enough, and you look at the change in the flexibility, sometimes you can actually figure it out by just looking, you know, with no error, what would be happening. It has to be that the damage is here, because the only way that I could get that change is like this. But if the structure is complex, okay, if the structure is complex, actually as soon as the structure gets a little bit complex, there's no way you can tell. And in the paper you will find examples which is sufficiently simple, but at the same time it's not possible to tell by looking, you know, things like this. It doesn't matter that the structure is determinate or indeterminate, right? That's irrelevant. And you have some sensors here like that, right? And then you get damage on this bar, let's say. And you want to know what is, hello? Hold it.